So now that we can integrate powers of trig functions, we can use trigonometric substitution to evaluate functions that involve the radicals the square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. Now you've seen some of these types of integrals before where back in Cal 1 where we had all of the pieces that we needed to use either a basic u to the 1/2 type situation, or where we had something like an arcsecant or an arcsine or an arctangent, and it just fit the beautiful form that we needed from those charts. So these are specifically going to be ways that we can handle ones that don't necessarily match that format. It'll work if they do, but it'll also work if they don't. So if you have one of these radicals of one of these forms and you don't know what to do, this is where you start. So for integrals that involve the square root of a squared minus u squared, we're going to use a substitution u equals a sine of theta. And we're going to build a triangle using the Pythagorean theorem that looks like this. For integrals involving the square root of a squared plus u squared, we're going to let u equal a tangent of theta. And we're going to build a triangle of this form using the Pythagorean theorem. And I don't necessarily recommend that you have these three triangles memorized. I think it's better to build them using SOHCAHTOA and the Pythagorean theorem. For integrals that involve the square root of u squared minus a squared, we want to let u equals a secant of theta and build this triangle. So the part that you want to know is which order of radical goes with which trig function. And keep in mind that the a should always be a constant, whereas the u is going to contain your x. So let's look at an example. In this one we have the integral of dx over x squared times the square root of 16 minus x squared. So if we wanted to try and just let this be u to the negative 1/2, our u would be 16 minus x squared, which means that u prime would be negative 2x. And I don't have the pieces I need to form that because I have x squared in the denominator and I don't have an x in the numerator or any way to cancel that with algebra, so I know I need to do trig substitution. So if a squared for this problem was 16 and u squared was x squared, this would be an a squared minus u squared square root. And if you go back up to your chart, you know that that means that u equals a sine of theta. So u is going to be x and a is going to be the square root of 15, which is 4. So u equals a sine of theta means that x is going to be equal to 4 sine of theta. And if I divide both sides by 4, I get that x over 4 equals sine of theta. Now why that's useful, we know from our SOHCAHTOA rules that sine of theta is the opposite over the hypotenuse. So I can build a triangle where this is my theta, the opposite would be the numerator x, and the hypotenuse would be 4. And in doing this, everything ends up in the right place. If we let this missing side be b, then we know that x squared plus b squared equals 4 squared. So b squared would be 16 minus x squared, and b would be the square root of that. So see, you can build this triangle without having to memorize those forms. Now, what we're going to do is we're going to take our integral piece by piece and we're going to replace all of the different pieces so that instead of in terms of x, they're going to be in terms of theta. So the first thing I notice is that I need a dx. And if we know that x equals 4 sine of theta, then dx is going to be the derivative with respect to theta here, which is going to be 4 cosine of theta d theta. So wherever I had a dx, I'm now going to write 4 cosine of theta d theta. So that's my dx. I also have an x squared, and instead of x squared, I'm going to write 4 sine of theta squared, because I know that x is equal to 4 sine of theta. The last piece here is the square root of 16 minus x squared. And that's the part that's a little bit trickier to find. You have to go back to the triangle. So what you want to do is you want to look at your triangle and you want to say, okay, where do I have the square root of 16 minus x squared and another side that happens to just be numerical with no x's in it? And relative to theta, that would be the adjacent side and the hypotenuse. So from the triangle, using SOHCAHTOA rules, I know that the cosine of theta, which is the adjacent over the hypotenuse, is the square root of 16 minus x squared over 4. And if I multiply both sides by 4, I get that 4 cosine of theta is equal to the square root of 16 minus x squared. So I can now replace that square root of 16 minus x squared in the denominator with a 4 cosine of theta. So now this is what we're going to be integrating. So I'm going to cancel what cancels. I notice I can cancel a 4 cosine of theta from the top and the bottom. And 4 squared is 16. I'm just going to bring out 1 over 16. And I'll have 1 over sine squared of theta, d theta. And I'm going to see what I can do to integrate this. Can I use trig rules from Cal 1? Can I use the concepts that we looked at in the previous section with powers of trigonometric functions? What do I know and what can I do? Well, one thing, I don't know an integral for sine squared of theta right off the top of my head, but 1 over sine squared of theta is the same thing as cosecant squared of theta. And that is a very common integration rule that you should know from Calculus 1. 1 over 16, the integral of cosecant squared of theta is negative cotangent of theta, and that's all going to be plus c. So if I just clean up my constants a little bit, I have negative 1 over 16 cotangent of theta plus c. Now we're not quite done yet. The last thing that we need to do is we need to convert back to x. How do we do that? Well, that's what this lovely triangle is for, and that's why we draw it. So I need to know what cotangent of theta is. I know that cotangent of theta, using SOHCAHTOA, that is the adjacent over the opposite. It's 1 over the tangent, which is opposite over adjacent. So if I look at theta, the adjacent here is the square root. Get to draw the square root of 16 minus x squared, and the opposite of theta is the x. So that is my cotangent of theta. So now I just come back over here and I say, well, I'm going to plug that in. That's negative 1 over 16 times the square root of 16 minus x squared over x, all plus c. And you might just want to take one more little step and make that negative square root of 16 minus x squared over 16x, all plus c, just to make it a little prettier. But that is my final answer. Make sure that you don't forget to convert back to x at the end. So I'm just going to zoom out on this a little bit and look at it start to finish. So we noticed that the first thing we did was we picked our substitution. So this would be my step 1 here. And then we built our triangle. That would be my step 2. And then from there, we converted to the integral in terms of theta. We integrated. We found the pieces that we needed, and we plugged them back in. So steps 1 through 5 in order. I know we kind of jump around the screen on this one a little bit, but that's the nature of these problems. Okay, let's look at another example. I've got the integral dx over the square root of 9x squared plus 1. So with this one, I have an a squared plus u squared or u squared plus a squared. It doesn't matter if there's a plus in the middle. But u here is going to be the part that has the x in it. So the square root of 9x squared is 3x. A is going to be 1. And we're going to substitute u equals a tangent theta. So 3x equals 1 tangent theta. And tangent of theta would be 3x over 1. And we know that this is the opposite over the adjacent. So if I'm building a triangle with theta, this would be 3x and this would be 1. Using the Pythagorean theorem, finding c, we would get the square root of 9x squared plus 1 equals c. So that's where our triangle comes from. So I've done that substitution. I need to now replace the integral with 1 in terms of theta. So if I know that x, coming from here, I know that 3x equals tangent theta. That means x equals 1/3 tangent theta. And I'm going to take the derivative of that. The derivative of tangent of theta is secant squared of theta. So I get 1/3 secant squared of theta d theta. So dx is now going to become 1/3 secant squared of theta d theta. The other piece I need is the square root of 9x squared plus 1. So the two sides of the triangle that involve that are the adjacent and the hypotenuse. And I know that I can use cosine of theta, which is adjacent over hypotenuse, to get 1 over the square root of 9x squared plus 1. So that means that 1 over cosine of theta, or secant of theta, is equal to the square root of 9x squared plus 1. So I'm now going to replace that square root of 9x squared plus 1 with secant of theta. So now we get to work. I notice that I can cancel a secant of theta, and I can bring out a 1/3. So I really have 1/3 times the integral of secant of theta d theta. And if you go back to your rules from Cal 1, the integral of secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta. So now I just need to convert back to x. So I'm going to need a couple of things. I'm going to need the secant of theta and the tangent of theta in terms of x. And in this case, we actually already have those because we know that the secant of theta is the square root of 9x squared plus 1. So I'm going to have 1/3 times the natural log of the absolute value of the square root of 9x squared plus 1 plus the tangent of theta, which is 3x. And that's all going to be plus c. So that will be my answer. So just to kind of zoom out so you can see the whole problem, we figured out our substitution, we built our triangle, we found the pieces that we needed, and we integrated and then converted back to x. This example is interesting because instead of having a square root, it has a rational power, but the concept is going to be the same because remember, 3/2 power is the same thing as saying a square root cubed. So we're going to make the same substitution based on the fact that we have a u squared plus a squared. So again, this is going to be a substitution using tangent. So I'm going to substitute u equals a tangent theta, and u is going to be x, and a is going to be 1. So x is going to be equal to tangent of theta. That's understood to be over 1. So my triangle theta, opposite over adjacent, looks like this. And if you use the Pythagorean theorem, you get the other side is x squared plus 1. Okay, so for our substitution, we know x, we need dx. So if x equals tangent theta, we know that dx is going to be the derivative of that, which is secant squared of theta d theta. So I will make that substitution. And this is really the square root of x squared plus 1 cubed. So whatever goes in there, we're going to cube it. And I know that I can use the adjacent and the hypotenuse, so we will use the secant of theta, which is the square root of x squared plus 1 over 1, or just the square root of x squared plus 1. So what I'm going to end up with here is the secant of theta cubed. Okay, So from there, we can just integrate and clean up however we need to. I've got secant squared of theta divided by secant cubed of theta. So this is the integral of 1 over secant of theta, d theta. And another way to write 1 over secant of theta is the cosine of theta. So it turns out this integral is actually pretty straightforward. The integral of cosine of theta is sine of theta. Now I know up to this point we have not mentioned sine of theta anywhere, but it's pretty easy to find it from the triangle. If you look at the triangle, we know that sine of theta is equal to the opposite over the hypotenuse, which is going to be x over the square root of x squared plus 1. So this now becomes x over the square root of x squared plus 1, all plus c. And that will be your answer.